Alright, dear students, welcome to Alchemist Academy. So this is the voice of the Brilliant, and during the course of this JAMB preparation, I'll be taking you through this. So let's hop directly into the topic of today, which is basically measurements and units. Measurements and units. So we see a lot of students today complaining about physics being a very hypothetical course. But the simple idea about physics is that once you get the concept, the basic concept, what to do will be easy. So yes, measurements and units in physics. This is a very crucial topic in physics, and students will, I think, unavoidably come across stuff like this. Questions on this immediately. So before we delve directly into measurements and units, like we all know what physics itself is. Physics is that study of that aspect of science that deals with the study of matter and energy changes. So physics basically talks about matter. It talks about two things, basically, matter and energy. To broad business. But before we even get into the aspects of energy, we have to know what matter itself is and what matter itself is. And today, if you ask all science students, they know what matter itself is. They'll be able to explain to you that okay, this is what matter means. So matter is anything that has mass and occupies. It's more like what we chorus every day in class. Matter is anything that has mass and occupies. But do you really understand what this thing itself is, what matter itself is? Well, matter is anything that has mass, actually. In some cases, there's a matter is anything that has weight. Anyway, whichever way you want it, matter is anything that has mass and occupied space. So now, physics is now solely interested in studying energy relation. Energy is studying what's called matter in relation with energy. So under matter, study two things. One, it occupies space. Matter has the tendency of occupying space. And of course, it has mass. Obviously, this is a form of matter because this, what you are seeing is capable of occupying a space. You can see that if I remove this thing from here, you can't find it here. So if I put it here, it has occupied a considerable part of this board. So it validates that truly matter is anything that has mass and what occupies space. And this mass, as you are saying, is just is that property of matter in which everybody in physics we use body, be it object, be it human being, be it car, anything. We can use body. We use body. Objects to qualify any form of matter. Get it done. So now mass is that property of, or is that part of matter, or let me say mass is what matter contains. Get it done. Is the property of matter in which every part of the body, be it this way, you get it done, it has a considerable mass in it. This what's called is massive in nature, or it has mass in it. So it's an inherent property of every form of matter. So that's just a little idea, or brief idea of what matter itself is. So before we go into measurements, we'll talk about measurements and units in physics. Measurements and units. And today most students have problems solving problems on dimensions. And because if you don't understand this particular stuff, you're likely not know what to do. So measurements and units. Measurements is just the process of assigning numerical value to what? To matter. You get it now? To matter. We talk of matter. You get it now? So it can be in the form of volume. You get it now? Block of centimeter, meter in that case. In the form of what? Length. We use meter, and in that manner, and so on and so forth. So measurements is just the process of assigning numerical value. And it is not only in physics that we use measurements. You can use measurements in biology. There's several aspects of life where measurement is very, very key. Yeah, now, so before we delve into dimensional analysis, I would like to talk about the what we call you know, quantities, fundamental quantities. Quantities. So you will all agree with me that even when I mention quantities, they are still what? They are still related to matter. So in physics, we use this term quantity, more like quantifying objects. You get it now? So we have 7 basic fundamental quantities. In most cases, we say basic quantities or fundamental quantities. So we have 7 basic or 7 fundamental quantities. So it's either you say fundamental quantities or basic quantities. They mean the same thing. So I'll just quickly list them out. And then the mnemonic we use for that, which is you get it now. Or you can simply say light matter. You get it now. The 7 basic quantities in physics. 7 basic, following the scope of O level. You get it now. We have luminous intensity, you get it now. We have temperature, you get it now. We have mass, we have electric current, we have time, we have amount, you get it now. And we have length, you get it now. We have luminous intensity, time, mass, electric current, temperature, you get it, and then we have amount of substance, is a basic quantity as well too, and likewise length. You get it now. So there's what we call unit as well too. You see, each of these respective quantities have the units in which we use to quantify them. You get it now. So for this, for luminous intensity, we use candela. You get it now, we use candela. For temperature, the simplest unit we use is Kelvin. There are other units in which we can use. So for mass, simplest unit we use is the kilogram, or simply kg. Get it now. For electric current, which is a very, very crucial quantity, we use the ampere. Get it now. Ampere. So symbolically, we have something like A, get it now. This one is kilogram, get it now, kg. Kelvin and this CD. Get it now. Then we have the temp, so we have time, seconds, simplest unit. Then we have the amount of substance, or simply amounts. We use what? N. Get it now, symbolically. Then we have what we call length as an important unit as well. So we use meter as the unit. Get it now. So these are the 7 basic fundamental quantities in physics. Now we also have what we call derived quantities. Get it now. Derived quantities. So we have the derived quantities. How we are getting it? So we have fundamental quantities, we have derived quantities. So derived quantities, like I said, fundamental quantities are actually the simplest quantities. You get it now? So derived quantities are all the other quantities. You get it now? All the other quantities that are different from what I've just listed. You get it now? All the quantities that are different from. So they depend on fundamental quantities. You get it now? They depend on fundamental quantities. So we have quantities like, we have derived quantities like force, impulse, work, and so on and so forth. So these are derived quantities. We have a lot of them. And during the course of this tutorial, I will during the course of dimension analysis, I will bring in some of the derived quantities we have. So moving on, like I said, quantities, quick recap, I divided into two, fundamental and what? And derived. Now, please mind you, we have other, what's it called? We have other forms of quantities. Now, this is following the system internationally, the units. You get it? Now, this is what they propose. You get it? Now, following them, this is what we have. Now, we have other quantities like supplementary quantities. But I will advise you not to disturb yourself about it because no one will ask you. Meanwhile, we'll still try to consider part of these quantities. I mean, when we are doing circular motion, you get it right? So we have supplementary quantities. You get it now? Radian and steradian. Radian and steradian. These are supplementary quantities in physics. You get it now? So they are just simply for plane angles and solid angles. Alright, so I hope you guys are following me. Now before we get directly into dimension and dimensional analysis, you get it now. We have three key quantities in physics. Three key quantities in physics that are useful in the analysis of all these other quantities. You get it now? They are simply length, time, and mass. Yeah, please take note of these three things. So we have length, time, and what? And mass. Remember I said length has the units, meter, this one seconds, and this one what? Kg. Please take note. So you see that in some cases you see it as kg, ms. You get it now? So just take note of this one. Because most of the derived quantities we'll be using, we use dimension, what's called dimension analysis for derived quantities. Yes, now for derived quantities. So please take note of these three things: length, time, and mass. So before we get into that, we have to know how they measure these three key quantities: length, time, and mass. How do they measure them? You get it? And which instrument do we use? You get it? So for length, let's quickly run through it. Length. Yes, now length. Now the length is measured in meter, like I said. It's measured in meter. And we have three basic instruments, large instruments we use for them. But the first one is the vernier caliper. Or no, the first one is the meter rule. We use the meter rule. Then we use the vernier caliper and the micrometer scale gauge. We use these three instruments to measure length. Again, they are very, very important instruments. And in the next video, I will take you guys through how to measure these these quantities. How to measure these quantities using these lab instruments. Okay, so that is the first one, length. Then let's consider mass as well too. Then let's consider mass. Okay, let's consider time. Some of the lab equipment we use for time. Okay, we use what? You can use the work and use your wristwatch. You can use your wristwatch. You can use your wristwatch. You can use your stopwatch. You can use the sandwatch, and so on and so forth. Measuring time. Then we have the one used for mass. You get it now? We have for mass and equally for weight. You get it now? For mass and weight. You get it now? We use the lever balance. For weight, we use what's it called? The spring balance. So we use the lever balance, get it now, and so on and so forth. Now these lab equipment, they have their working principles. So in our next video, now take you guys through how to use vanilla canvas and others. Then I will I will explain explicitly how to use them, and of course the working principles. So now quickly, let's run through dimensional analysis. Dimensional analysis. How you guys are getting it? Dimensional analysis or dimensions. Like I said take note of these three things: length, time, and mass. But before we even move on, I want to explain a few things to you guys. There's what we call there's what we call distance, things to note. Things to have knowledge about before ever trying out dimension. Displacement, speed, velocity, time, acceleration. So it is important that you take note of these three and these what's called 1, 2, 3, 4, 5, 6. Take note of them before ever considering dimensions. So the first one is distance. Get it now? What is distance? So assume you have something like this, point A, point B. Get it now? Point A, point B. Then point C. You get it now? These points from here to this place, get it now, is simply your distance. So distance is measured in what? In any direction. So it could be from here to here, or from here to here. Get it now? From here to here, or the change in position in any direction. That is simply distance. The change in position from any direction. So it could be from here to here. In fact, it could be from here to here. Let's say you have another point D. It could be from point A to this place. Get it now? From here to here. In any direction. That is the word. In any direction. You get it now? And in most cases, let's assume this is Peter. Moving from here to here. So we can say, or from here, just point A to point B, we can say Peter has covered 2 meters. You get it now? We say 2 meters. You see terms like that, 2 meters, 2 kilometers, terms like 2 centimeters in that manner. You get now? They simply highlight the distance covered. You get it? So distance is just the change in position in any direction. You get that? In any direction, like I said. Now, when we talk of displacement, displacement is simply the change in position of a body in a specified direction. Change in position of a body in a specified direction. In a specified direction. Please take notes. Take notes under in the realm of physics. These two are quite related, but they are different. You get it now? This distance and displacement are quite related. In most cases, you see something like S for distance, X for displacement. And in most cases, they will still use meter, X meter for both. But by definition, we have the displacement to be a change in position of the body in a specified direction. What do I mean by specified direction? Okay, let's say considering this cardinal point. Get it now? Considering this cardinal point. Normally, we have this north, south, east, and west. So assuming a body is moving from here, get it now? Assuming a body is moving from this point, get it now? Moving from this point, then on getting to this place, changes direction to this point. Get it now? So let's say this is a body, then changes direction to this point. Get it now? Now we can say the body has covered what? In fact, we can measure this angle. We can measure this angle to be theta. So we can say this person, let's call this person Peter. Get it now? Let's say Peter has covered a distance of 30 meters in this direction. So in most cases, you see something like 30, or in most, you see something like north 30° east, north theta degree west, north theta degree what's it called? Or you can say south theta degree east. Get that? This represents the displacement of the body. Get that? In a specified direction, we are being specific that Peter has covered a distance of, let's say, 30 meters. So this 30° in most cases can even be 30 meters. Like here, Peter has covered a distance of 30 meters in this northern direction. Get that? In this northern direction. So we are being specific here. Get that? We are being specific. Remember I said in the case of distance, we just talked about the change of position of the body in any direction. But for displacement in any, in a specific direction, we are being specific. You get that? So now there's something I want you guys to note as well. So you see, I want you to take note of something very quickly. So let's say I said this is 30 meters. This is simply explaining distance, right? And when I say not 30° east or 30 meters of west, you get it now? 30 meters of west. You can see that I'm still repeating this 30 meters in this case. Again, but the only difference is that I've only mentioned west here, meaning I'm being specific. So we say in physics, let's say note distance, or let's say the value of distance. The value of distance is the magnitude of displacement. It's the magnitude of displacement. Yeah. Magnitude is simply talking about size. Yeah. So this value you are seeing here is also repeated here. So this same thing, yeah, this value you are seeing here is repeated here. So we say distance is the what's called is the magnitude of displacement. So take note of that. Then moving on to speed. Moving on to speed. You get it now? Or before speed, time is the interval. You say time is the interval between two points. In physics, we respect time a lot. Yeah, now we respect time a lot. Be it if you are probably talking about motion or anything. We talk about these things with respect to what? To motion. So we respect time a lot. So time is simply the interval between what? 2 points, 2 different points. So assuming you have this point A and point B, and you have someone moving from this point to this point. Let's say this person intended, what's it called? Moving from this point to this point here. Get it now? This person must move in a specific. You have to measure the time. Again, seconds is a very small unit. So there's no way this person will move from here to here and won't the time conscious. Then we respect time. So time is simply the interval between what? The 2 points. The interval between 2 points. That's simply time. Then speed. Again, now speed in physics is speed and velocity are quite related. Now, so just like we have distance and displacement to be related, but one particular difference. Again, so speed, we say speed is the change in distance. Distance over time. That is speed. Distance over time. So velocity is given as what? Velocity is given as what? Displacement over what? Over time. There's a reason for this. You get it now. Speed and displacement. You understand this better when next class when we're talking about scalars and vectors. You get it now. So you can see that speed and distance. We are using distance to explain speed, using displacement to explain velocity. It is to tell you that speed is scalar in nature. You get it now? Speed is scalar in nature, distance is also scalar in nature. Velocity is what's called is a vector quantity. You get it now? Velocity and displacement, they are both vector. Now, why speed and distance are scalar? There is a reason for that. During our next class, I will explain that to you. So we are solely concerned about dimension and dimension analysis in physics. So moving on, dimensions. Now that you have the knowledge of these things, we now want to put them into application. We want to see how they apply in the course of dimension. You get it now? So very quickly, let me write this here. Speed, distance, over time. Velocity, displacement, over time. Let's take note of something. I said distance is measured in meters, right? Distance is measured in meters. But can you also think of other things that are measured in meters? So we say position. Position of a body in meters. Yes, you can measure position of what's it called? Let's just simply say position. Measured in meter. Then of course length. I want you guys to have this idea that it's not just distance alone. You get it now. Length as well in meters. Height. And use them in meters. Breadth in meters. You get it now. Width in meters. So how you guys are getting that? You get it now. So in this case now, we talk about the LTM. So in most cases they call it the LTM principle. You get for dimension or simply dimension. You get it now. So if length and distance can have the same meaning, definitely it is safe to say our length is measured in meters. So right, it's for this. You get it now. So please take note of that. Then moving on, our time is measured in what? In seconds. While our mass is what? Is in kg. You get it now. So let's take these things into consideration. So speed and velocity. In fact, the other time I mentioned quantities that can be measured in meters. I forgot to add displacement. Of course, you can measure displacement in meters as well. So that is why speed and velocity are used interchangeably. They are related, so related. But the only difference is that speed and distance are quite related. They use distance to measure speed. Get it now? Because okay, I will explain that in the scalar and vector class. The displacement and velocity are the same what? The same. And that's why I use displacement to measure what? Velocity, and they are equally what? Vector quantities. Yeah, so let's say for speed. Remember distance is measured in meters. So you can say meter, and simply say meter over what? Over time, till second. So that's why you use something like meter per second. Okay, now. In mathematics, if this one is coming up, it's going to something like -1. Yeah. So if this one is just something like this, it's simply something like m times 1 over s. That is the meaning. Is equal to m times x over. That's how to do. And when you multiply both together, I've got like ms minus 1. Get it now? So, likewise, velocity. Get it now? Now, moving on. So I've just shown you. Now, in the case of dimension, again, in the case of dimension, your L will still retain, or your length will still retain this length. Again, your length will still retain L. So in the case of dimension like this now, you can have distance to be in meters, you can have length to be what? In meters. Again, so in the case of dimension like this now, if you want to solve this one using a dimensional analysis, you just simply say your distance, you let your distance retain its L symbol. Get it now? You let your distance retain its what? It let L symbol. So in that case now you say L over what? And your time will retain its what? T symbol in the case of dimension. There are several ways of doing things like this. Yeah, so in that case now, what will now happen is that now it will be something like this. It's equal to what? Length times 1 over what? Over t. You get it now? Then it's equal to, let me do this one. Is equal to LT inverse. You get it now? This is, look at it very well. LT inverse. This is for speed. And likewise, velocity. You get it now? So that is just simply dimension of speed and velocity. So both speed and velocity have the same, let me put that way, speed, LT or ms inverse, velocity, LT or what? Simply ms inverse. And let's move on to acceleration. Let's move on to acceleration. In physics, we talk about acceleration. We talk about velocity. Here, we talk about acceleration and velocity. Now, acceleration, you know, let me use an illustration here. So let's say you have a boy moving from this point to this point. So let's call this point A. Let's call this point B. Take note of talking about velocity again now. Velocity. You get it now? The boy is moving from this point to this point in a linear direction. Okay, now simply on linear motion. This person is moving with a constant velocity. Is moving in this direction. So if this person, normally the person is maintaining this speed, this velocity in this direction. Again, is maintaining this velocity in this direction. So if this person now decided to move in this direction, get it now? We can now see it has increased its velocity. Now, increasing velocity we are talking about is the acceleration. Normally, when this wave was moving, it was moving in this direction, constantly moving until it got to this position. Now, after getting to this position, it now decided to change its direction, moving in this path. Yeah. Now, the increase in velocity now is what we call acceleration. Yeah, so acceleration is mathematically given as. Acceleration is simply given as what? Change in velocity about change in time. In most cases, velocity can also be given as what? Average speed, or velocity or average speed. In most cases, average speed. Yeah. So your speed, you can say average speed or average velocity. It's given as change in velocity over time or change in time. Yeah, for your average speed. You get it now? In that case now, you're changing changing distance. Change in distance. Or simply change in x. Let's use x. Change in x. So in that case now you have something like the change will now be something like x to x minus over t2 minus t minus. You get it now? That's for your average speed. Now same thing is applying here. Acceleration is just the increase in velocity. It could be an increase in velocity or decrease in velocity. When acceleration is increasing, or when velocity is increasing, we call it acceleration. When it is decreasing, we call it deceleration or retardation. Again, so change in velocity now is now giving us v2 minus v1 over what? t2 minus t1, and it's still the same thing as velocity over time. So now to get the dimension of this, of acceleration, dimension of acceleration. Yes, now the dimension of acceleration. It's simple. We know what velocity itself is. Like I said, both velocity and speed have the same dimension. So it's just simple. It's what's it called? In that sense, it is wise to say, okay, just bring your velocity indirectly without even having to discover yourself again. We know that our velocity is what? LT minus 1. That is velocity. You get it now? Then over time, you see, you get it now. The rate of change of velocity with time is what? Is acceleration. The rate of change of what? Of distance with time is velocity or speed. You get it now? So in this case now, like I said, we respect time a lot in physics. Okay, so this is LT raised to power minus 1 over t. And now moving further, you have something like this. If you express further, you have something like LT minus 1, then LT minus 1 times 1 over t. This is the limit. Get it now? This is the meaning. 1 over t. Get it now? Because this one means over 1. So you can just simply separate them. And like I said, following the law of indices, you now have something like LT minus 1 times what? T. If this t is coming up, then it will carry minus 1. You have that LT minus 1 minus 1. Get it now? Or simply minus 1 plus minus 1. Get it now? Minus 1 plus minus 1. And in that sense, it will be LT raised to power minus 1 minus 1. And that is what? LT raised to power minus 2. Get it now? LT raised to power minus 2. And that is for acceleration. That is simply for what? Acceleration. This is what you get for your acceleration. You are getting it now. So now, moving further, you can now express your LT raised to minus 1 as, or you can bring it in this form as well. So in that case, you can see the same thing as well, meter per second square. You get it now? Meter per second square. This what you are seeing here simply means m over x squared. That is the meaning. You get it now? M over x squared. If you bring this x squared up, you still have m x raised to minus 2. And so we use meter per second square. And in most cases, the right is as something like this. This sign means per second square. Hope you are getting it. So acceleration in that sense, acceleration in that sense is given as what? LT raised to minus 2 or ms raised to minus 2. So for speed, we say meter per second. For velocity, meter per second. What this means is that this is the rate, speed is simply the rate of change of distance with respect to time, or per second, or per time. Or in a specified time interval. That is the meaning. So acceleration is given as LT raised to minus 2 or ms raised to minus 2. So let's try two other examples before we now check our past questions to see if these things are truly correct and fun. To see if they are truly correct and what and fun. So let's try for work. Let's try for work. Work is given as what? Force times distance. Now work is given as force times distance. But then we know that, okay, let's use D. So you don't get confused. Again, let's use D. Force times distance. In most cases, we use S or D for distance. You understand that in the equation of motion very well. So work is equal to what? Force times distance. But then you don't know what the dimension of force itself is. So it is now, what do? We express further. We express further. We now say our force is now what? Force is now given as what? We know that force is equal to what? Mass times acceleration. Force is mass times acceleration. Now, from our expression, we know the symbolic representation of mass already. We said we use m, capital M. So capital M times. Now, our acceleration, going back to this. Going back to this. This is it. LT raised to minus 2. So we say LT raised to what? Minus 2. Just bring it in. And if you want to express, if you actually want to express from the beginning, probably you are doing bio exam and you need to express from the beginning. It's just as simple as bringing it back from speed. Now, acceleration, you still remember, acceleration is what? Velocity over time. So you express velocity first. Velocity is distance over time. Distance over time. So you express, after you are done with this, then whatever you get, you bring it in here to get your acceleration. And after that, you bring it, that's if you want to express completely. Okay, let's do that. All I'm saying is that you really don't need this one in JAMB. Again, no one is checking how how expressive your work is. So let's say you want to solve for force. Force is mass times acceleration. You get that? Acceleration is what? Acceleration is given as what? Average, what's called? Velocity over time. That's the acceleration. Your velocity, but you don't know what velocity, you don't know the dimension of velocity. Let's assume you know it before and you forgot to. So it's just easy, it's simple as saying you find the dimension of velocity first. And you know your velocity is what? Distance over time. You get it now? Velocity is distance over time. From what I said earlier, you can use this symbol for distance. You get it now? You can use it for distance, you can use it for position, you can use it for length, you can use it for breadth, you can use it for height. You get it now? You can, provided as the case may be, you can use capital N for distance, for displacement, for position, for height, for breadth, you know, in that manner. Alright, in that manner. So we now want to bring it in here. So this is our D. Then you bring, sorry, it is L. Again, it is L. So you bring it in here over T. Remember I said use T, the symbol, use capital T for time in dimension or in dimensional analysis. Again, so you have something like LT raised by -1. Following the law of indices, we bring this up and put -1 at the top. It's not like you have something like A over B, because of AB minus, AB minus, you are getting now 1 over S is the same thing as S raised by -1, according to the law of indices. So now we've gotten the dimension of velocity. Moving on to acceleration, you know what this dimension is now. So back to acceleration now, you know that our velocity is what? L raised by -1. Our acceleration will now change to what? V over T. Whatever you get in velocity, you bring it in here. So that will be L raised by -1 over what? Remember our T, use capital T for it. That's our time. And that will be LT raised by -1 times 1 over T. You get it now? The same thing as saying LT raised by -1 times T raised by -1. Solving using the law of indices. You know, these are two similar variables. In that case now, you see your L, open bracket, what? T raised by -1 plus what? -1. This is just simply mathematics. That is, you have L, open bracket, what? T raised by -1 plus -1, that is -2. L times, open bracket, T raised by -2 is the same as what? LT raised by -2. You get it now? So eventually, you've gotten your dimension for acceleration. So you know what acceleration is, L raised by -2. You know what your velocity is. Now, coming back to work. Force times distance. You get it now? You don't know what force itself is. So you now have to solve for force. Force is what? Mass times acceleration. You know what to use to represent your mass already. Now, then acceleration. So in that case now, remember I said for length, for all these quantities, displacement, distance, displacement, position, height, breadth, in that manner, length, use capital L. In dimension, use capital L. For time, use capital T. For mass, use capital M. So that's why in most cases they call it the LTM principle. LTM principle. So now, back to this one. Use our capital M. We have used capital M times what? This capital M, then times acceleration. Anything you get in acceleration, you bring it in. That is LT raised by -2. LT raised by what? -2. You are getting that? So it's now going to be MLT raised by -2. So this is the dimension of force. MLT raised by what? -2. Now you can as well write it in this form. kg, remember your mass is measured in kg. It can be kg, then your length is a meter. You get it? Your length is a meter. Then your time, you measure the unit is seconds. It's going to be what? S raised by -2. You are getting it now. So it could be this or this. Then these are for these two, what's it called? These two expressions are the dimension now what's it called? quantification for force. Here now for force. So moving on, we've gotten for force now. This is for force. Now what will be for work? Get now, you have to know what will be for work. Because initially you don't know what the dimension of force will be, but you know for D that normally this is distance. And distance here is represented as L. Here and it's represented as L in what's called under the realm of dimensional analysis. So now that we've known the dimension of force already, get it down. So our work becomes what? First we bring in MLT, MLT raised by minus 2. Get that raised by minus 2. That is for what? For force. Now what will now be for distance? M minus L. You get it now? So we now say it's equal to. Now MLT raised by minus 2. In case you probably didn't see this well. Raised by minus 2. You get it now? Remember in under your law of indices. Okay, now if you have to consider, if you have to add the powers of what's called two variables, they have to be similar. Yeah, so you can't just add the power of m and l because they are not similar. So in that case, now what will happen is you have something like m t minus 2 times or open brackets. Now you want to consider these two l because they are similar. Okay, now you have to be very careful at this point because they are similar. It's now going to be L times L. Again, now it's going to be what? L times L. So remember, in your law of indices, if you have A times A, it will be what? A squared. Because anything raised by this power, for you to, in law of indices, A simply means A raised power 1 times A raised power 1. Again, you have to be careful. A raised power 1 times A raised power what? 1. So, according to the law of indices, these times will change to what? It will change these powers, it will add up these powers. So, since they are similar, you just bring one out, it's equal to what? A, you get it now, raised power 1 plus 1, and that was A squared. That's why you got for A squared. If it's something like B times B, it's same thing as B squared. Still following this principle, just your normal law of indices. You are getting here. So, that's because they are similar. But you can't say something like A times L is equal to AL squared. That's wrong. Because they are not similar. They are not similar. So this rule will only hold for two similar variables. So that's what is going to happen here too. So in that case, now I now say it's equal to what? MT is power minus 2, open brackets. L times L. That is L raised power 1 plus 1. You get it now? That is what? L raised power what? 2. Then it's going to be what? MC raised by minus 2 L squared. Now you can rearrange ML squared T raised by minus 2. You get it now? This is the dimension for work. You get it now? That is the dimension for work. This is the dimension for what? For force. Now this one can also be written as, you know, this is mass. Yeah, now this is mass. This is mass. So it's going to be kg. This is length. Again now, meters. Use m squared. And this is time. See s raised to the power minus 2. So still the same thing. So MLT. So now to write that, let's simply put that in. We add to our equation. So our force is what? MLT is by minus 2 or kg ms is by minus 2. For work is going to be what? M L squared t raised by what? Minus 2 or what? Kg m squared s raised by minus 2. So that is it. Now you can as well proceed to solving others. We have surface tension, viscosity, in that manner, pressure. And let's take, for example, for surface tension, it can be force over length. Again, and since you know that the surface tension, let me clean this up. Force over length. Surface tension is given as force over length. You get it now? Now, for what's your force? You have it as what? MLT is per minus 2 over length. Get it now? Over length. Over meter. Get it now? Over length. Remember, I said length. Get it now? So you just simply solve. You can do that for this. Then as well too, for pressure. You know, the first thing to do, the first thing to do before you, now I want you to take note of something. You can see that we are using actually most of these variables we are using right from speed. Right from speed. We have to use a few of the fundamental quantities. Length, time, and mass. Obviously, they are. Remember the mnemonic LT, mental. You get it now? Length, use length, use time, I'll use mass. LTM. These are the three things. You can as well continue. That's for advanced cases. You get it now? There are cases where you use electric, what's it called? Electric current, use luminous intensity for advanced cases. But following the scope of O level, we treat LTM as what's it called? For dimension. Yeah, so the first thing to do is that you know the formula. Yeah, but how do you know the formula? It is as a result of the of the consideration of all these fundamental quantities. Without these fundamental quantities, there is no way we come about with all these things here. So all this speed, velocity, acceleration, force, work, surface tension, pressure, they are called derived quantities. They solely depend on these quantities we are seeing. So without these quantities, there is no way to come up with this one. So for pressure, you have something like force over area. In that manner. That's how you get. So let's quickly check few of our JAMB questions, and you see that these things are actually real.